In this video, we will begin implementing our neural network library. At first, we will go through the design of the library, then we'll implement the layer and layer list classes, we'll implement a few activation functions that we discussed last video, and we'll round it off by implementing the forward pass through the neural network. I would strongly recommend you try and implement the classes and functions we discuss before you watch me do them in the video, as this will help solidify the theory we discussed in the previous video. All the code will be posted on my GitHub, which will be linked in the description down below. Now, without further ado, let's get into the design of our library. We're first going to write two classes, layer and layer list. The layer class will represent a single layer in our neural network module. The layer list class will represent the entire neural network model. After we're done initializing the classes, we're going to write three activation functions, which we discussed in the previous video. We're going to cover ReLU, Sigmoid, and Softmax. Now, this Wikipedia link has a lot more activation functions that you should go and explore and try implementing by yourself. After that, we're going to tie everything together and implement the forward pass of a neural network. Let's get started with initializing the layer class. I'm going to write the constructor method, and we're going to take in a couple of parameters. So we're first going to take in the input size. So this will be the number of neurons that are the inputs to the current layer. The output size, which will be the number of output neurons in the layer. An alpha value to specify the learning rate of the model. An optional bias term, which we'll set to false by default. A batch size term, because we want to train the model in batches. And finally, an activation function, which we'll set to be none by default. We'll start off by initializing attributes in the layer class to store each of these values. So self.input size is equal to input size, and so on. Now, let's also store the weights and biases of the current layer in a NumPy array. This will be self.weights is equal to np.random.rand and self.input size, self.output size. This is going to create a NumPy array instantiated with random values of shape input size by output size, and this will represent the weights. Now, if there is a bias term, looks like I forgot to include an attribute to store the bias term, so we'll add that in. And next, if there is a bias term, we're going to include another row in the weights matrix to store the bias values. So we'll do that as follows: self.weights equal to np.vstack. This essentially stacks two matrices vertically. So we're going to update our weights parameter and add on a row of random values representing the bias terms. np.random.rand 1, self.output size. And that's the entire constructor for our layer class. Let's now write the constructor for the layer list class. Once again, and we are going to take in a list of layers in the initializer list for the layer list class. And we're going to store the model as a list of these layers. We're also going to add an append method so that if we want, we can add additional layer objects to our model after the initialization. So this would again look like this. And for layer in layers, self.model.append layer. Now let's also write a couple of getter and setter methods for these classes, which will become useful later on when we're implementing other parts of our library. We'll first write a getter method in the layer class called getBatchSize. This function will return the batch size of the current layer. And we'll also write a def set alpha method, which will set the alpha value in the current layer to be this new alpha value. Let's say new alpha. The reason we're doing this is that when we're training, if we're getting close to our optimal minimum solution during the gradient descent algorithm, we might want to reduce the alpha value so as not to overshoot the minimum. And similarly, we'll need to write a set alpha value in the layer list class because the layer list class is going to control the alpha value of every single layer in the module. So we're going to write set alpha. We're going to take a new alpha value and we're going to iterate through all the layers in the self.model list. So that would look as follows. For layer in self.model. And for each layer, we're going to call its set alpha method as follows and pass in the new alpha value. So that's the basic structure of our layer and layer list classes. We still have to implement the forward pass, but we will do that after we're done implementing a couple of these activation functions. Now, as we discussed in the previous video, if we did not have activation functions in a neural network, then all that the neural network would be able to recognize is a linear function. Now, activation functions work by taking in the matrix product of the inputs and the weights of a layer and passing them into a nonlinear function, for example, ReLU, Sigmoid, and Softmax, and returning the output of that function as the layer output. So let's take the example of ReLU. ReLU is defined as, let me put it in as a doc string. ReLU is defined as a function, so we can write it as f of x is equal to a piecewise function which will return 0 when x is less than or equal to 0, and it will return x when x is greater than 0. Let's put some more spacing here. So this is what the piecewise function ReLU does. And as you can see, it's nonlinear in that there isn't a single line that describes this function. There are in fact two lines. When x is less than 0, that is on the left half of the coordinate plane, the value output by ReLU will just be 0, and on the right half, the value will just be equal to x, which would be the same as the line y equal to x. Now, the reason we'd want this is if we have a layer where we only care about outputs, if the output is positive, then we would use ReLU to cancel out all negative outputs of a layer. So to implement ReLU, we're going to define this dunder method, def call, and we're going to pass into it the pre-activated output of a layer. And what we want is that for each value in the pre-activated output, we run this function f of x and return the results. So since this is essentially an if-else condition, we can use the np.where function defined in the NumPy library, which handles that condition and returns the corresponding value. So we're going to say where pre-activated output is less than 0 or less than and equal to 0, we're going to return 0, and otherwise we're going to return 1, and we're going to multiply this with the pre-activated output. And this is the NumPy array that we're going to return. Essentially what this does is if the pre-activated output is less than 0, then we're going to multiply it with 0, essentially canceling it out. Otherwise, we're going to multiply it with 1 or retain its value. Now, the sigmoid function is similar. The sigmoid function works as follows. It takes an input x and it returns to you the value 1 divided by 1 plus e to the negative x. The implementation is very straightforward. We once again write our call dunder method. We pass in the pre-activated output. And we return this exact formula. So 1 divided by np.exp, which is essentially going to take the exponent of pre-activated output. That's the sigmoid function. Similarly, we're going to define the softmax function. And we're again going to take the pre-activated output. And one thing we have to keep in mind is that the softmax function is unlike our previous two activation functions, which acted on each value in the activated output matrix. Softmax, on the other hand, acts on all the values in the pre-activated output. Let's say that the pre-activated output is equal to 1, 2, 3. Or let's just make this -3. Now, if I pass this to ReLU, then the output I would get would be 1, 2, 0. Because 1 is greater than 0, 2 is greater than 0, while -3 is less than 0. So only -3 gets cancelled out and the others retain their value. On the other hand, if I pass this into softmax, he's going to do a couple of things. He's first going to create a matrix where he raises e to the power of each value in the pre-activated output. So it will become e squared, and e to the -3. After that, he will calculate a denominator, and that would be the sum of all values in this matrix. So that would look as e plus e squared plus e to the -3. After this, let's just write this as exponents. And after this, what he's going to do is he's going to return exponum divided by denominator. So essentially, the first term would look like e divided by this denominator. The second term would look like e squared divided by this denominator. And the third term would look like e to the -3 divided by the denominator. Now, the reason for this is that the softmax function is usually used to convert a list of layer outputs into possible probabilities. And this is often used as the last layer's activation function in a classification task. So we're going to implement this slightly differently. What we're going to do is we're going to define a variable called x_shifted. And we're going to say this is np.exp, which is essentially e to the power. And we're going to say pre-activated output minus np.max pre-activated output. And we also want to do this on the axis equal to 1 and keep the dimensions equal to true. So what this axis parameter is saying is it's telling the function to act on the first axis, which is all the rows of the pre-activated output, and keep dimensions is ensuring that the value or the matrix returned by np.max is of the same shape as pre-activated output, which would allow them to be subtracted. So if we break this down, what this line of code is doing is simply finding the maximum value in the pre-activated output, which in this case would be 2. Next, it's going to subtract that value from each value in the pre-activated output matrix. So the matrix would become -1, 0, and -5. And then it's calculating x shifted as this matrix, e to the -1, e to the 0, and e to the -5. Now, if we finish off the function, we can see exactly why it's doing this. We also will store a value called denominator, and this will simply be the sum of x shifted. So that's just summing all of these values, and we're going to return x shifted divided by denominator. Now, this is equivalent to finding the value of softmax as explained here, and it's a little bit of exponents and manipulating exponents, but then you can easily prove this to yourself. But this is equivalent. And the reason we're doing this is, let's say that the value in the pre-activated output matrix was a large number, let's say 2000, and then we had 0. What would happen then is that this value 2000, if we take e to the power of 2000, we would get a very large value. In fact, the value is so large that Python would classify it to be infinity. And if we get infinity in our calculations, then it's likely to propagate through the model and we're going to get incomprehensible results. Because obviously you can't multiply anything with infinity or add anything to infinity, so that would just throw the entire model off. By shifting the exponent, that is by subtracting every value with this max value, we would get 0 and negative 2000. E to the 0 is simply 1, and it's not a very large value, and it can be handled by a model. And if we have e to the negative 2000, well, that's a very small value, and Python will approximate that to be 0. And since softmax is essentially trying to assign probabilities to the values, we obviously expect the pre-activated output with value 2000 to have a much greater probability than the value 0, and this would make sense because 2000 would be given a probability of 1 and e to the negative 2000 would be given a probability of 0. This issue, where raising e to a big number could lead to an infinite value being generated, would also appear in the sigmoid function. So one more thing we have to do here is assign pre-activated output to be equal to np.clip pre-activated output negative 1000, 1000. So what this is doing is it's going through each value in the pre-activated output matrix, and if there's any number smaller than negative 1000, it'll just get assigned the value negative 1000, and any number greater than 1000 will get assigned the value 1000. And those are all the activation functions that we will write in this video. I would suggest you try and implement a few more activation functions from the Wikipedia page. A couple I would recommend would be the binary step function and the tanh function. Now, returning to our layer and layer list classes, we can now implement the forward pass of the neural network. We'll implement it similarly using a called under method. And we're going to take the layer inputs as the arguments to this class. Then what we need to do is a very simple matrix multiplication. As we discussed in the previous video, we simply need to multiply the layer inputs with the self.weights, and this will give us the expected output for the layer, and that would just be it for the forward pass. The only thing is that we have a couple of edge cases to handle. The first one is if there is a bias term, in order to ensure that the two matrices match. So let me just write down the shapes of the matrices that we expect. We expect layer inputs be of shape batch size by self.inputs. Or let's just say input size. Input size. And we expect our self.weights to be input size by output size. Now these shapes obviously match because we're multiplying these two matrices, and the number of rows in the second matrix is equal to the number of columns in the first. Now, if there is a bias term, however, the self.weights matrix will have another row in the matrix. And to account for that, we need to add a column of ones to the layer inputs. So if there is a bias term, then our layer inputs would become equal to np.hstack. So this is going to stack two NumPy arrays horizontally, and that's what we want to do when we want to add a column of ones. So this is going to be layer inputs here, and np.ones shape would be self.batchSize, which is what we stored here in the initialization function, comma 1. Now we can do this matrix multiplication. And finally, if the layer does have an activation function, remember we initialized it to not have any activation function by default. Now, if it's not none, that is there is an activation function, then we have to call that activation function on the layer output. And this will be our new layer output. And that's what we will return from this layer. So what this called under method is doing is it's going to first change the shape of layer inputs by adding a column of ones if necessary, that is if there's a bias term. Then it will use matrix multiplication to calculate the pre-activated output. After that, it'll pass it into an activation function if there is one for the layer. And finally, it will return the layer output to the calling function. Now the calling function will be implemented in this layer list class. We're going to define another call here. The call method will take an input. We'll call it model input. We'll assign it to intermediate results. And then for each layer in self.model, we will pass in the intermediate results matrix, and we'll assign the result from the layer back to intermediate results. Essentially, what this is doing is it's taking the input to the model, passing it into the first layer, getting the result, and passing that result onto the next layer, and so on. So this is essentially completing the forward pass through the layer. And at the end, we're going to return intermediate results as the final result of the model prediction. And that's it. That's the entire forward pass through a neural network. Let's quickly test it out. I'm going to write the if name double equal to main if statement to test this bit of code within the layer file. We're going to define our model to be a layer list. So this is going to be a model, and we're going to have just two layers in there. Let's have one input and one output in the first layer. We'll not add any bias terms. And in the second layer, we will take one input and get two outputs. And then for activation function, let's give it softmax. Now, in order to use the softmax function, which is defined in the activations.py file, we're going to just import all the activation functions using the syntax from activations, import star. This is going to import all the activation functions we defined in this file. With this model, let's just give one input. So np.array, let's give it one input of just one, and we'll call this int. And now, if we use this syntax, model imp, we're going to pass this input matrix into the model, into this call function, and we're going to get the results after it passes through both of these layers as the output, which we can print. To see that this is working, let's just add a couple of print statements. Here, we're going to print self.weights to view the weights in the current layer, as well as print the layer output here because we want to view softmax in action. And with that, let's just run the code. Oh, oops. Looks like I forgot a couple of things. So the alpha and batch size values here are not set to any values by default. So we need to pass that in when we define the layers here. We'll just set alpha to be 0.1 because we don't really use it yet. We're going to use that when we do the back propagation in the next video. And we'll set the batch size to just be equal to 1. Same thing here. Let's just fix the spacing and let's run this. Tuple object cannot be interpreted as an integer. Oh, okay. So this just takes the shape as a list of variables. It doesn't have to be passed in as a tuple. Similarly here, we just pass it in as separate arguments and not as a tuple. And yep, let me just clear it and run it again. So the first values that we see here, the weights of each layer, the first layer has a weight equal to this, and the second layer has two weights with these values. Next, when we ask the model to predict the output for an input of 1, that's going to be passed through the first layer, where 1 is going to be multiplied with this weight. So the output is going to be 0.9386, the same as the weight. And next, when it's passed through the second layer, the first output would be this value multiplied by 0.2, which should give us 0.19. And the second value will be 0.93 multiplied by 0.69, which will give us 0.647. Next, if we convert these into probabilities using the Softmax function, we should get these values. So if we wanted to calculate that by hand, the first value should be e to the power of 0.19. The second value should be e to the power of 0.647. And let's just store their sum here. And the values will be this divided by the sum. I'm going to just say s is this divided by s. And this will be this divided by s. Let's just quickly check this in the Python interpreter. So we'll say s is equal to, or we should say from math import exp. I'm importing the exponential function from the math library. I'm going to store s as equal to exp 0.19 plus exp 0.647, and we'll say print exp 0.19 divided by s, which is 0.38769, which is close enough to what we got here. And if we print the other value, exp 0.647 divided by s, we get 0.6123, which is the same as what we got here. So that shows that the activation functions we wrote work, and so does the forward pass through our neural network. Now, we could, of course, test the other activation functions and the bias terms and whatnot, but I'll leave that up as an exercise to you guys. I'll see you all in the next video where we implement backpropagation in our neural network library.